Hello everyone, my name is Jana and I'm from the Czech Technical University in Prague, and today I will present our work titled Identity Verification from Human Scent using channel representation of 2D gas chromatography mass spectrometry. This is a joint work with colleagues from Czech Technical University and University of Chemistry and Technology in Prague. So let me start with the motivation. Why would we even consider scent as a biometrics? People emit chemical signatures that can be distinctive and to some extent stable over time. This gives scent a few practical advantages over classic biometrics. It doesn't require the subject's active participation, it doesn't rely on line of sight, and it can tolerate certain environmental noise. Importantly, scent traces can also persist, which enables delayed acquisition and reanalysis. And looking forward, there is the prospect of sampling at a distance using electronic gnosis. Altogether, this makes scent promising for scenarios where traditional biometrics are hard to deploy. Now, the key question is how do we turn chemical measurement into something that modern machine learning can use reliably? We work with two-dimensional gas chromatography coupled with time-of-flight mass spectrometry. Conceptually, this technique separates and identifies chemical compounds in complex mixtures. It uses two chromatographic columns in series with different stationary phases, which is complementary, often near orthogonal separations. The output has two retention time dimensions. The first column gives T1, and then the periodic modulator slices the effluent and injects it into a faster second column, producing the second dimension T2, which lies within modulation period. We get a structured 2D retention time map that we can treat like an image, with rich spectral information at each location. Finally, we apply a binary mask to keep uniform dimensions and suppress acquisition artifacts. Formally, you can think of one measurement as a grid of pixels over the T1, T2 plane. For each pixel location U, we do not store just a single value, we store a local mass spectrum, which is a set of mass-to-charge ratios and corresponding intensities. So the raw data are high-dimensional and irregular in a way that is inconvenient for standard image processing pipelines. On the right, the bottle panel shows a 2D intensity heat map over the T1, T2 plane, and the zoom-ins illustrate that even when spectra look nearly identical, as here for heptacosane and nonacosane, the chemical compound is often distinguished by its location in the chromatogram. Now, let me briefly introduce the dataset that we present and make public. We evaluate on Human Scent Dataset, which contains 2,528 samples from 252 individuals. A subset was already published as the 4DC dataset. The dataset is approximately balanced by biological sex, with 129 male identities and 123 female identities. On the right, we summarize the dataset statistics, including the distribution of samples per identity, ranging from a few measurements up to several dozen, with roughly 10 samples per identity on average and median around 10 samples. Practical detail is that the dataset was measured using two different time-of-flight mass spectrometer detectors. The one stores measurements in 10-bit values and the other in floating point values. Here, you can see the number of measurements per identity. Most subjects have around 9 to 10 samples, but counts vary, so our evaluation has to handle uneven samples per person. Now, the core idea of this paper is what we call a channel representation. The raw mass spectrum in each pixel is variable length, so it's not directly compatible with standard convolutional neural networks. So we compress it using a bank of overlapping learnable basis functions. We define a set of basis functions Vk, each with a learnable amplitude and parameters. Each basis function assigns a soft weight to every local mass-to-charge peak. We multiply that weight by the corresponding intensity and sum over peaks to obtain one channel. Doing this for all k and all pixels yields a channel-encoded image C. Intuitively, each channel is a smooth learnable bin over mass-to-charge rather than the hard histogramming. In our implementation, we use Gaussian basis function as illustrated on the right. The Gaussians define overlapping weighting windows over the mass-to-charge axis, and the resulting channel values are aggregated intensity sums. The parameters are learned self-supervised by reconstructing intensities with a weighted mean square error objective. We also experimented with a triangular as a basis function. Now, a related question is whether we need explicit registration. In gas chromatography, instrument conditions such as temperature changes and hardware drift can shift retention times, which misaligns compounds and can make comparisons unreliable. We therefore compare a pipeline without registration to a pipeline with registration to a canonical frame which was already presented. The registration procedure follows 4 steps. First, we detect compound peak locations using a reference mass spectrum and a chosen detector. Second, we build a Delaunay triangulation over the detected peaks. Third, we compute a coordinate transformation via barycentric interpolation mapping the detected peaks to reference locations. And finally, we do piecewise linear interpolation to obtain a canonical grid. With the channel representation, verification is simple. We learn an embedding function f that maps each measurement to a d-dimensional vector. For CNN-based embeddings, we train f using a margin-based triplet loss, so samples from the same identity are pulled closer and samples from different identities are pushed apart by at least margin gamma. At test time, for any pair of measurements, we compute a dissimilarity between their d-dimensional embeddings. This is the pairwise score, and then threshold that score to decide whether measurements originate from the same identity or not. For the embedding function itself, we experiment with multiple choices to understand what works best. We evaluate 3 hand-engineered descriptors, locally binary patterns, histogram of oriented gradients, and scale invariant feature transform, adapted to our channel images. We also evaluate 5 pre-trained CNN backbones with a lightweight projection layer. ResNet 18, ResNet 101, VGG16, Inception v3, and Google LANet. Finally, we design a custom CNN specifically for this data. It has 3 modules. First, a convolutional backbone that uses anisotropic 2x8 kernel motivated by the structure of the measurement grid. Second, a downsampling stack. And the third, a residual MLP head. The idea is to respect geometry of the T1, T2 axis rather than treating the input as a generic natural image. Now, let me summarize the results. Using the channel representation with our custom CNN embedding, we reach 89.5 area under receiving operating characteristic and 53.3 true positive rate at 5% false positive rate, evaluated with 10-fold cross-validation. Across the evaluated setups, CNN-based embeddings perform better than the chemistry-style baseline and the traditional handcrafted descriptors. We also observe that explicit spatial registration is not necessary in this dataset. The performance with and without alignment is very similar. Finally, the anisotropic 2x8 kernels in custom CNN improve performance, while standard pre-trained backbones remain competitive. On this slide, the table reports area under a receiving operating characteristic and true positive rate at 5% false positive rate for every embedding method under each alignment setting. You can see that the same top performing methods stay at the top across columns, and the differences between alignment variants are smaller than the differences between embedding choices. So alignment has a limited impact here, while the choice of embedding model drives the performance. Before I conclude, let me be clear about the limitations. First, our accuracy is still well below established biometric modalities, such as iris, fingerprint, or face. Second, we have not yet validated generalization across different labs and real-world conditions. Third, long-term performance and month-scale drift are not quantified in this study. Finally, the finding that the canonical registration is unnecessary is not demonstrated anywhere else. It was demonstrated only on our HSD. Robustness under strong retention time drift and in settings requiring higher cross-site consistency remains to be evaluated. To conclude, we propose a learnable channel representation that converts GCxGC ToF-MS measurements into a compact multi-channel image, and we show that the modern embedding techniques, particularly a custom CNN, make identity verification from Human Scent feasible at the meaningful accuracy levels on the Human Scent dataset. Thank you for your attention, and using this QR code you can see our project page.